Hey, this is Hunter, and this is Rotational Energy and Momentum Free Response Question Review number 1. The diagram shows a top-down view of a frictionless tabletop. So you could think of this maybe as ice, has a small hole in the middle here. We have a small block connected to a string whose other end passes through the hole and is held on by a person. The block performs uniform circular motion and a small circle clockwise around the hole. So it starts to go around the hole, starts at A, goes to B in a circular path. As it goes from B to C, the person inside lets that string kind of loosen up and it comes out to this and then goes from C to D. So we're going to look at the uniform circular motion here to here, and then we'll see that there's uniform circular motion here to here. But from this point right here over to this point here, something funky happens, okay? This is not uniform circular motion. That part would be something else. So we're going to try to kind of figure out what's going on there. So it says the diagram to the right shows the point P at an instant during the time the string is being lengthened. So as you're lengthening it from this point right here, which is B, until it hits point C, something weird is happening. You'll see that the velocity vector is tangent to the line, and when we do that at each one of these points, we do not get a straight line, okay, coming back to the center like we do at C or at B. You'll notice that the velocity is tangent and it is perpendicular to the center. Okay, but we don't have that along that BC line. So this is kind of an ingenious little question that they have here. They want to know what happens to the block as it travels from point B to point C. So as it's going from B to C, you'll notice that the velocity vector is not perpendicular to the radius, and that is to the force. And because of that, we are going to say that the kinetic energy decreases because the velocity doesn't make a right angle here. Neither does it right here. It does at point C, but from B to C, it does not do that. It gets closer and closer to it as it gets to C, but it's pretty far out. And so the kinetic energy here decreases because the velocity does not make a right angle with the force at P. How about the angular momentum at about point O? That remains the same. And the angular momentum remains the same because there's no torque since that force is pointing towards the center, okay, around that rotation point. So that is the reason why for both. Now you have a frictionless tabletop that has a frictionless wall attached to its surface. So this would be a wall that's extending out towards you. It'd be kind of like if you took a Hot Wheels track and set it up on edge, and then you put a car and you made the car go around. So that's essentially what they've done is they've put something in here, and it's just a block, and they push the block and it starts to move around this curve. So at this point, we'll see that the normal force is pointing perpendicular to the surface at any point, and our velocity is always at 90 degrees from that. So there's nothing pointing towards the center. Because there's nothing pointing towards the center, this kinetic energy for this one now will remain the same, but the angular momentum about point O will increase. So why is that? The force is perpendicular to velocity, so the velocity cannot get bigger or smaller. The force points to the left, okay? That causes a clockwise rotation that increases the angular momentum. So you'll notice that this block has a kind of a clockwise rotation. So it's going to rotate in this direction as it goes around. So you'll see that it points differently as it goes through. And that is the end of very strange question number 1.